let's play. So we're looking at the integral test for series. And let's see, some things that are important when we're doing that. So we have some sum where we have these a sub n's that we're trying to add up. And we're hoping there's a related continuous function, f of x. Some things that are important about f of x is f of x would need to be continuous, at least most of the time, for us to take the integral, right? Other things about it is we want it to be positive, otherwise we're going to have some cancellation issues. And then we also want it to be decreasing, because if it's not decreasing, then we're going to fail the divergence test, which means there's no point in even doing this at all.
But there was something else attached to decreasing.
Oh, the monotonic and having a limit, is that what you're talking about? Yeah, so we had another theorem from last week, the monotonic convergence theorem, that says if a function is, if a sequence is sequence, not series, if a sequence of numbers is monotonic, means strictly increasing and strictly decreasing, and there's a bound, not necessarily, then there has to be a limit. Is that what you're thinking of, maybe? Which is a slightly different idea than this. But here, the bottom line is we have the divergence theorem we talked about before, and the divergence theorem says if the limit of, as n increases, of your a sub n's, if that ain't 0, it diverges. If it is 0, what do we know? We know nothing. If it is 0, it makes it kind of a candidate for convergence, but you never know until you do more work. So the integral test gives us a chance to do more work to check it out. So if we happen to say, oh, the limit's 0, and the terms are positive, that means it must be decreasing. So we have a chance to use the integral test, which is what we did the other day. So for example, we looked at recently the sum of the 1 over n's. That would be related to the function f of x equals 1 over x. And in which case we would want to be integrating 1 over x with respect to x. And we did this a long time ago before. If we take this from anywhere to infinity, then we're going to find this thing diverges, right? On the other hand, we looked the other day at the sum of the 1 over n squareds. Related function would be f of x equals 1 over x squared. And we found that when we integrated from somewhere, let's say 1, to infinity of 1 over x squared, that went to, I think it went to 1, if I remember right. This one right here is infinite. Yeah, that diverges. That does not converge. Yeah. Yeah, and we looked at that the other day in class too. So I'm giving some examples relating back to these ideas right here. Whatever a sub n is, we rewrite it with x. That needs to be a continuous function, needs to be a positive function, and it needs to be decreasing. If it's not positive and decreasing, then we're not going to have this to be true, which means it's going to diverge, so why bother? Okay. So we use the integral test for when we find that the limit of the individual terms does go to 0, which means we don't really know anything about it. So the integral test gives us a place to learn some more. And that's what we're going to spend the next couple of weeks on, trying to learn more if a series, to try and figure out if a series converges. We're going to take this a step farther today by looking at, can we estimate the error when it does converge? So in class the other day, we found out that the sum, let's use a different subscript, let's use k. As k went from 1 to infinity of 1 over k squared, we found that this converged. And we let Desmos take it out to 100, 200 terms to kind of see where it was heading. And we'll do that again in just a moment. When it converges, we usually call the convergent value S. So we say S equals that sum. Okay, so this is the actual sum. What we know is it has a limit. We're calling that limit S, but we don't know a special name for that number. Is it related to pi? Is it related to the square root of 2? Is it some proper fraction or improper fraction that we've seen before? We don't know that yet. We usually look at what are called the partial sums, right? A partial sum means stop somewhere. So for example, S sub 10 would be the sum as k goes from 1 to 10 of 1 over k squared, which written out would be 1 plus 1 over 2 squared plus 1 over 3 squared, all the way up to 1 over 10 squared. And we can ask GeoGebra, not GeoGebra, Desmos we've been using to add those up for us. So I'm going to go do that. So I'm just going to drop in here. Let's see, I'm using an I here. So I raised to the second power. And I can go click on that point, and it says it's about 1.55-ish. Right, up to 10. Yep. I can go out farther if I want and then track those points, but let's just do 10 for the moment. All right, so according to this program, it's about 1.55. Let's see, approximately 1.55. And there are lots of other programs we can use to do this. I like doing it in Desmos because I can picture the points moving along, but oftentimes I might just type into some other calculator like Wolfram Alpha and just tell Wolfram I want the sum of 1 over k raised to the second. I'm hoping it'll recognize k as my variable, and then I can say let k go from 1 to 10. Sometimes you need to tell it what the variable is, like maybe say k. And a TI has similar notation if you have an older version of a TI. The new version has this cute pretty print, right? And so I type it in, blow it up, and it looks like it guessed right, and it's about 1.5-ish. Wolfram Alpha does an amazing job of giving me a reduced fraction if I ever happen to need it. That seems kind of insane, but hey, it'll give it to me. It's kind of cool. Excellent programmers there over at Wolfram. All right, let's see, where were we? Back here. Okay, so in general, a partial sum can stop anywhere. It doesn't have to be 10, it could be 100, it could be 5. So usually we say S sub n stopping at some number, could have been 10 or 100 or whatever. So in that case, my sum would be k equals 1 to n of 1 over k squared, which just like above, 1 plus 1/4 squared plus 1 half squared plus 1 over 3 squared, all the way up to 1 over n squared. Now, anytime we stop, we're missing out on that infinitely long tail. Okay. Now, the nice thing about these series right here, these terms are decreasing. That means every little piece in the tail is getting smaller and smaller and smaller and smaller and smaller. Okay. So the farther out I go with n, my tail is getting less and less and less. But that tail is also important. So I want to talk about that tail a little bit. So the tail, better known as the error, is the actual sum minus any partial sum that we take. That's supposed to say error. So what term is after n? Well, it would be n plus 1, right? So we just pick up at n plus 1 and keep going. So it would be the sum as k goes from n plus 1 out forever of 1 over k squareds, which would be 1 over n plus 1 squared and 1 over n plus 2 squared, and never stop. Right? But that never stopping thing is a problem for us human beings because we have to stop. So I want to draw a picture of what that error looks like and see if we can find a way to say, hey, I bet I can kind of say it's about this. All right, so we've got some function. I'm going to break the axis so we can look out at the tail. The function has to be decreasing, has to be positive, otherwise we can't apply an integral test to it. And so let's say the function is dropping down, kind of like that one right there. And then out here somewhere I have n. After n is n plus 1. After n plus 1 is n plus 2, and so on down the line. And I need a copy of this. C, Control C, V. Oh, darn, I missed. Again. Okay, I need 2 of these to show you what we're going to do. So let's see. So the black curve right here, that would be my f of x version of this thing. My little terms I can look at in a couple of different ways. I could take a look at them as right-hand endpoints, in which case I would have a bunch of rectangles underneath like this, all the same width, believe it or not. Let's make that sucker a little wider so it matches its compadres there. And they're just going to keep going out here to the right forever. Okay. I could draw them also with left-hand endpoints, in which case they would look like this. I kind of have my choice here as to which way I want to draw it. Now, just a note, the area of each of these rectangles, since this endpoint happens when n at n, then that area right there is the term a sub n. And this guy right here, that's the term a sub n plus 1. This guy right here would be the term a sub n plus 2, and so on down the line. Over here, I just flipped them a little bit. This right here is a sub n. This one right here is a sub n plus 1. This one right here is a sub n plus 2. And what I'm concerned about is my error. And how did I define the error before? Well, I said the error was the sum from n plus 1 on. So that would be a sub n plus 1 plus a sub n plus 2. Keep going forever. Okay, so that's everything after my nth term. So that would be those rectangles right there, right? Because there's n plus 1, there's n plus 2, and so on. How does the integral compare? Well, since the rectangle starts with this one right here, then I'm just going to basically draw a line. And if I want to compare f of x, right, f of x is this black curve, then my error as a sum would be comparable to the integral from n to infinity of f of x dx. And which is bigger here, the error or the integral? The integral is bigger because it's above the rectangles, right? So the integral is greater than my error at that point. If I look at the picture down below, again, I'm interested in the terms n plus 1, a sub n plus 1, a sub n plus 2. So if I draw my line, that line gets drawn right there. And I have, to the right of that line, I have my error represented, which is the a sub n plus 1 area plus the a sub n plus 2, and so on down the line. But I also have the function and the integral represented here too, right? There's f of x, and I have the integral, this time from n plus 1 to infinity, of f of x dx. And how do the error and the integral compare in the second picture? The integral is smaller, right? So here the error is less than that. Oh, drew it the wrong way. Control Z, the integral is less. There we go. So what I have here with these two pictures is the error is trapped between the integral from n to infinity in, come on, pen, and the integral from n plus 1 to infinity. So this is what's called the integral remainder theorem for sums. So integral test remainder, we can box in that error. So the error is going to be between the integral from n to infinity of f of x dx and the integral from n plus 1 to infinity of f of x dx. So if Melissa starts making those dares again like she did before, like I dare you to get within 100,000th of the actual number, I can use this relationship here to try and zoom in on the error approximation. Now, it doesn't give me the exact answer. It just says the error has to be somewhere in this range, right? So we're just going to calculate that for the function that we're playing with right now. So we're playing with f of x equals 1 over x squared. And so for now, I'm just going to say, hey, let's look at the integral from a to b of 1 over x squared. And then we have an infinity to plug in, which we can't do directly. We got to do a limit. And then either we're going to use an n or an n plus 1. So I'm just going to call it a for now. Antiderivative. So let's see, that's x to the negative 2. We would add 1, give us x to the negative 1, divide by negative 1. So an antiderivative here would be negative 1 over x, right? Evaluating that from a to b is going to give me negative 1 over b minus negative 1 over a, so plus 1 over a. And then ultimately our b needs to be infinity. So if I take the limit of that sucker as b goes to infinity, one over b goes to 0, leaving 1 over a is all I need to worry about. So that means for my particular sum, let's pick on, we just did the 10th partial sum a few minutes ago with the calculator. So S sub 10, right, that was 1 plus 1/4 all the way up to 1/100th. And we got approximately to 2 decimal places, 1.55-ish. When we rounded that, the error for that, well, that would be 1 over 11 squared plus 1 over 12 squared going to the right forever, right? So that's the problem. It keeps going forever, which means I can't actually calculate the whole thing. All we know is that it's a fixed number. We just don't know which number it is yet. So we know here that my error has to be less than this integral right here. Well, that means a is n. Oh, cool. It has to be less than 1 over n. Now for us, what's n in this case? 10. So it has to be less than 1/10. And the error has to be greater than, let's see, 1 over n plus 1. That would be 1 over 11. All right, so let's whip those out. Let's say I know 1/10 off the top of my head. That one's pretty easy. It would be 0.1-ish. And 1/11th, I think, is 0.09. Is that right? It's a little smaller than 1/10. 0.090909, if I remember right. So 0.09-ish. It's actually 0.91 if we round to 3 decimal places. Error. So the error is somewhere in there. So worst case scenario is I'm overshooting this by 1.55 plus 0.1, or I'm down the other way. So another way to think about this is if I take S sub 10 and I add that to the error, what do I get? So I take the first 10 terms and add it to the rest of the terms. Don't I get the actual sum when I do that? Okay, so since I added S sub 10 to the middle here, I have to add it to both sides there. So then I think it's about 0.55, 1.55-ish. So if I add that to this side, I'm going to get 1.65. And if something doesn't look right about this inequality, if I add it to the other side, what do I get? If I call it 0.909, that's going to be what, a 4 there, and carry the 1, that's going to be a 6, that's going to be a 1.64. Something looks illegal about what I just wrote. Well, the partial sum plus its error is the actual sum. That is true. All right, we'll go with it for now. But I can put a boundary on that error. Why does that seem off? Let's see. If I take the 10th partial sum plus the 10th error, that should give me the actual sum. All right, we'll come back to it. I need my brain to wrap around that for a sec. All right, let's try another problem. So playing around with some other things, we looked at p-series the other day. P-series is something of the form 1 over n to the p as n goes from 1 to infinity. And we found, playing around with integrals, that there were some conditions we could say, hey, this converges or diverges. And we found that if p was less than or equal to 1, we have divergence. And we found that if p is greater than 1, we have convergence. So if p is 1, right, that's the harmonic series that diverges. It doesn't go down fast enough. But if we make that denominator just a little bigger, then it'll converge. So question, what if I tried this? N goes from, I'm going to have to start at 2 for what I'm going to do right now, 1 over n times the natural log of n. Now the natural log of n grows wicked slow, but I'm multiplying by n. But it does grow. So the question is, does this product in the denominator grow enough to let it converge? Okay, so I don't know. Let's take a look. So usually what I do is I just play around listing a few terms. So I'm going to go to my GeoGebra partial sum calculator. And let's see, I have 1 over I times the natural log of I. And, oh, it's not even on my screen. Oh, I started at 1. That's a problem. What's the natural log of 1? Is 0. 1 over 0 is trouble. So, ooh, there she is. Okay. So, and we could then bring it out a little bit. We could even go out even farther, like 100. And then we can change our scale and see where we're at. Let's see, X, take it out to 100. Ooh, 100. And then let's see, it looks like it's somewhere under 3 perhaps. Come here. And maybe 0. Okay, so here is, well, it's still got kind of a slope going on to it. Kind of reminds me of the natural log a little bit, that I'm not really so sure it's convergent. And I could do the next 1,000 terms and see. And I can always do something like ask Wolfram alpha, which is a little faster. And this way I don't get to see them, but I can get an answer quicker. So k times the natural log of k, close the denominator, start at 2. Be careful with your denominators where you start, especially with natural log is, because then otherwise Wolfram would probably have made a calculation but given me imaginary numbers, which would have been wild to see. And let's go out to 1,000. That might exceed its free computation ability. Ooh, it gave me a number. It gave me the 2.7-ish. That looks, in my picture, we went 100, and we seem to be in that ballpark. All right, maybe it does converge. All right. Let's see. What's the first thing we should do with a series besides list out a few terms? Excellent. Apply the divergence test. What's the divergence test say? The divergence says, well, just forget about the series for a minute. Look at the sequence. What happens when you take the limit as n goes to infinity of 1 over n times the natural log of n? Well, I have a denominator that's increasing. Numerator's fixed at 1, so this is ultimately going to 0. Does that help? Not really. Might diverge still, might converge still. Okay, so given our work with integrals in the regular p-series, this is a twisted p-series. Let's try the integral test, since that's what section we're on. Makes sense. So we want to look at the integral as x goes from 2 to infinity of 1 over x times the natural log of x dx. Okay, a couple options. Let's see, thinking back, we have an integral table we could look it up in. We could just ask some computer program. We could try u substitution or integration by parts. Good idea. I was thinking that too. U substitution. So let's let u equal, yep, natural log of x. So du would be 1 over x dx. And behold, 1 over x dx is right there. Nice. All right, so what do we got? We've got, then this now can be rewritten as the integral. I'm going to ignore the boundaries for a minute. And we have the integral of 1 over u du. And antiderivative for 1 over u, natural log of u. I'm going to wrap it for just a moment. What is u really? It is the, we have the natural log of the natural log of u from 2 to infinity. Now we really can't put an infinity up there, so we're going to have to put a b for now and then run a limit on that. So that's going to give us the limit as b goes to infinity of the natural log of the natural log of b. I get enough parentheses there, bing, bing. All right, and then minus the natural log of the natural log of 2. Okay, well, natural log of the natural log of 2 is the natural log of the natural log of 2, whatever that happens to be. And okay, let's see. Now we can move limits into and through functions and additions, subtractions, multiplications if those things behave nice. By behave nice means their limits exist. They're continuous functions over the area we're taking the limit. Well, the natural log is a nice continuous function, so we could bring that in here. In which case, what happens to the natural log of b as b goes to infinity? Natural log, it's going to infinity slowly, but it's heading there. Okay, and then its partner outside says, hey, you're going to infinity. Guess what I'm going to do? I'm going to go to infinity too. Very, very, very slowly. Okay, so those guys are slowly, 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 slowly going to infinity. Darn. Hate that. What's that mean here? Does this converge or diverge? It diverges, yeah, it diverges. The integral has an infinite amount of area. It's very slow growing. As we saw, like we looked at 100 terms, it was 2.7-ish. 1,000 terms was 2.7-ish. Am I lying about that? Let's see. I didn't actually click on that point there, did I? Oh, it's 2.3-ish. Yeah, another 900 terms, we gain 0.4. It's slowly growing forever, very slowly. All right. So bummer. So the multiplying the natural log into the denominator wasn't enough of a push to make this shrink fast enough to go to 0. So we might say, well, let's push it just a touch harder. So what if instead, there you go. What if instead we there you go. We said, oop, no, I don't want an integral yet. Gary, stop it. We took the sum as n goes from 2 to infinity of 1 over n times the natural log of n, but we square that natural log. Let's multiply another natural log into the denominator. See if that's enough of a push. Okay, so analogous function. So I'm squaring just the natural log.
Well, how you not
How do I know to do that? I'm just messing around. I'm trying to figure out how hard I have to push 1 over n to get it to converge. We know multiplying by n does it, right? We just did that one. But can I push it less hard and make it converge? Like, where are the boundaries of convergence and divergence? So that's where interesting math happens, those edges of weirdness. So that's what we're exploring right now, this edge of weirdness. So yeah, this is the edge of weirdness. The edge, called that weirdness. It's really true. A lot of times people will do math and they'll say, oh, it works good here, but it doesn't work good there. And then they stop and they don't really look at that intersection point. What's really going on at the intersection if we zoom in on it? So that's what we're doing here. We're zooming in on this intersection of convergence and divergence. Where does it break? Is it crooked? Is it straight? I don't know. All right, anyway, so function. We need to consider the integral as x goes from 2 to infinity of 1 over x times the natural log of x squared dx. And that u substitution went so well before, I think we should try it again. And so I'm going to say, let's let u equal the natural log of x. And then du is equal to 1 over x dx. And this is all looking lovely, right? Here's my 1 over x dx. So I now have the integral, and I'm going to ignore the boundaries, or I guess I can write them in as x's, but I can't plug them in yet, of 1 over u squared, right? Du. Let's see, 1 over u squared, that antiderivative is just negative 1 over u, right? Well, that's better than before, I think. This is looking promising. 1 over u, let's see. Ignoring boundaries for a minute, u is really natural log of x. And then we're going from 2 to, I'm going to have to throw a b in there so I can do a limit. Let's put a b there too. All right, so next we're interested in the limit. So new page, we now have the limit as b goes to infinity of, let's see, that was a negative, right? So we have a negative 1 over the natural log of b minus a negative, so plus 1 over the natural log of 2. I think I got that right. And let's see, can we sneak in there? If we sneak in there, we've got b is getting big, so the natural log is slowly getting big with it. So we have negative 1 over a bigger number. That goes to 0. Ah, we found an edge. So this limit is 1 over the natural log of 2. Interesting. So multiplying by just the natural log wasn't enough, but the natural log squared, that was enough. So if we did a natural log cubed, that should work out fine, and so on. And I'm just kind of curious about the natural log squared. What does that sucker look like anyway? Let's see. The natural log of x and squared. Ooh, kind of what does that look like compared to y equals x? And the natural log of x. All right, so let's move you over. So we can see, x, it grows pretty straight. Natural log grows wicked slow. Natural log squared goes a lot faster than the natural log does, but not quite as fast as a linear function. Okay, so when we had 1 over n, we multiplied the denominator by another n. That extra linear growth was enough to push it into convergence. This green function didn't grow fast enough to push into convergence, but the red function did. So the next question would be, well, what functions in between these two are strong enough to push 1 over n into convergence and which ones aren't, right? Because isn't there a lot of space in between those two, right? A lot of space there too. So it gets kind of interesting. We're not gonna, we could spend all week just playing with that boundary, but we're gonna stop there. All right, that was exciting. Let's try another one. There was a cute one in your homework. Oh, this one right here, yeah, there it is. Okay, so we want to find out if this integral converges or diverges so that we can compare it to the sum down here. Okay, so it's the sum of 5 natural log over n to the 6th. All right, so ultimately we're interested in the sum as n goes from 1 to infinity of 5 times the natural log of n over n to the 6th power. And you might say, well, why not apply the divergence test? That should always be your gut reaction. You see a sum, you think divergence test. So before I continue with the integral test, I'm going to say, hey, does this diverge? Let's just get this done. What happens when I take the limit as n increases of 5 natural log of n over n to the 6th? What's your gut reaction on that one? It goes to 0. Yeah, we were just looking at a graph of the natural log versus n, and n grows way faster than the natural log, right? So if this was natural log over n, it would converge. N to the 6th grows way, way, way faster than n, so it should just crush the natural log in terms of as they fight each other out to infinity. If you're in doubt about that, what would you do next to this if you were like, oh, I'm not really sure? You could plug in a few numbers, take a look, see where it's heading. Yep. What else could you do? What other tools do we have in our belt for these kinds of limits? Starts with an L. L'Hopital's rule, yeah, because technically this is infinity over infinity, and we can apply L'Hopital's rule to that. L'Hopital's rule says, well, take the derivative of the numerator, take the derivative of the denominator. Their rates of change give us a similar, the same limit basically as the functions themselves, is what he proved. So if I apply L'Hopital's rule there, I usually write a fancy L above my equal sign. The derivative of the natural log is 1 over n. The 5 is just hanging out, doing nothing. And the derivative of n to the 6th is 6 times n to the 5th, right? And we have the limit as n goes to infinity. And cleaning that up, it becomes pretty darn clear that this is 5, 6 times the limit as n goes to infinity of 1 over n to the 6th, which definitely goes to 0. So it proves our intuition. N to the 6th grows way faster than the natural log, which forces this sucker to go to 0 because the denominator is just kicking butt in growth over the numerator. Okay, so divergence test didn't give us anything, but you should always start there because that's like the easiest test there is. And if it says it diverges, you're done. Stop looking. But this says look more when you get a 0. Look elsewhere for help. And so we're going to look at the integral test. So we want to know what's happening with the integral as x goes from 1 to infinity of 5 natural log of x over x to the 5th power dx. Use substitutions looking a little sketchy here because the derivative of the natural log is 1 over x, and there's definitely a 1 over x, but there's a whole bunch of other x's too that I have to contend with. So I'm not sure I want to do that one, but it might work. Oops, wrong button. My next option would be, I think, integration by parts, which is harder than a use substitution. So maybe I will give a use substitution a shot. The problem actually said hint, integration by parts, but I'm going to ignore the hint because I'm stubborn. All right. So what if I did try that? U equals natural log of x. So then du equals 1 over x dx. And when I try to sub back in here, what happens? Let's see. I've got a u there in the top. I have part of my du covered, but I'm going to be left with an x to the 4th dx. Solving this for x means I'll have an e to the u on the other side. And then I'll have x equals e to the u. So I'll have e to the u to the 4th power, so e to the 4u. U over e to the 4u. I'm no better off. I just traded the problem for e to the x. Yeah, I don't know. I think let's do substitute integration by parts. Okay, integration by parts. Int by parts. We need parts, not parts. Parts. We need to come up with a u and we need to come up with a dv. So let's see. Derivative of the natural log is pretty easy, right? So I'm thinking maybe this is going to be natural log of x, because then du is just 1 over x dx. Okay, that means v, we could pull the 5 out. Yeah, let's just pull the 5 out, not worry about that. So then that means dv has to be x to the negative 5th, or 1 over x to the 5th dx. And so that means v would be what? Negative 1/4, sorry, wrong direction. X to the negative 4th. Yep, that looks right. All right, so what do we get when we rewrite that? Let's trash some things on the screen to make room. And shift these guys up a little. Oops, I missed. All right, so we now have 5 times uv. So that's going to be a negative natural log of x over x to the 4th. And we're also going to have an over 4. So there's my uv minus 5 times the integral of v du. So we get another negative there, so we can cancel. And then v du gives me, we'll have a 1/4 hanging out. And then that's really 1 over x to the 4th. So it looks like I have an x to the negative 5th dx. I get that right? Yep, that looks right. Ooh, that's nice. I can handle that. And again, this is going to be evaluated from 1 to infinity, 1 to infinity. So altogether, what are we going to get? We're going to get a, I guess I could factor out that 5/4, can I? It's everywhere. Oh, wait. Yeah, it's okay. Factor out the 5/4. We'll have a natural log of x over x to the 4th. Man, I hope this thing converges. It's a lot of work. Plus antiderivative for x to the negative 5th is, that's this guy right here, right? Negative 1. So we're going to have a negative 1 over 4x to the 4th. Oh, that looks okay. From 1 to infinity. All right, and then we have to take a limit of that one, right? So let's see. As x goes to infinity, what's happened with that? What's that? Oh, I messed up a negative somewhere. Let's put that negative right. Actually, everything's negative now. So I could just pull it out here and get rid of that one, but I had an error, sign error otherwise before. Yeah, otherwise this should have been negative, that's negative. Okay, I think that'll work now. Okay, so thanks for pointing that out. What's happening with this first fraction as we go to infinity? Is x to the 4th going to be growing way faster than the numerator? Yeah, so this sucker is going to go to 0 for the top boundary, and this clearly goes to 0. So now we just have minus plugging in 1 there, and that clearly looks like a real number. So this limit appears to be negative 5/4. And then we're going to have a minus each of those guys. So that's going to be, natural log of 1 is 0, so that's gone. So inside I'll have a negative 1/4. So it looks like the limit here is 5/25. Super important. That is not the answer for the sum. Oh, sorry, 5/16. That was weird. I was thinking ahead. 5/16. That's not the limit of the sum. All I know is that my sum is smaller than this integral, and this integral converges. At least part of my sum is, the part of the tail is. So this just tells me I have convergence. Okay, so by the power invested in me by the integral test, the sum as n equals 1, again, goes from 1 to infinity of 5 times the natural log of n over n to the, what was it, fifth? Is that where we started? Yep. N to the fifth converges. I have no idea to what. The next thing I would do to try and figure out what is I would start generating partial sums. So that's always another big question. To what do we converge? We have no idea. The only thing we can do is start looking at partial sums. What do we do after we look at the partial sums? Then we start looking at the error in the tail. So we can use the integral test to approximate the error. So we look at partial sums and error next. So we're out of time for fun today. We'll do another error problem tomorrow. And I'll double check that we did that last one right. I think we did, but something at the end there just looked a little odd to me. And that's it. Have fun with your homework. It's mostly, does the integral test apply? Does it tell us convergence or divergence? And there's one question at the end of your homework that asks you to apply that remainder theorem that we just went over. So have fun. We'll rehearse more of this tomorrow, and then we're going to move on to what are called comparison tests tomorrow.